Good morning, guys, and welcome to Physical Science. Today is May 6th. And as I mentioned before, and hopefully you guys know that the exam is still on Tuesday, May 11th. The review will be open starting from tomorrow, and it's going to end on Monday evening, okay? So that's, again, the same trick with the review in a sense that it's going to be graded. It's going to be graded as participation grade, regardless of how you do in the in it. You're going to get full credit if you start it, and that is to encourage you to do the review. And the exam is going to open on Tuesday morning, and I will be available during the time of the exam. At least during that time. After that, I have classes. So if you have issues with the exam and I don't respond to you immediately, and that is because I'm busy, hopefully you start it immediately when it's open. And usually I do not respond to requests within one full exam period, basically, which is about an hour and a half prior to its ending. So when it's supposed to expire, okay? Because there will be not enough time to notify everybody else that something is wrong or something else, okay? So that is basically in a nutshell what's going on with the exam. Today is the last chapter that is actually due for this exam. So we need to go through this chapter, and it's all about organic compounds, organic chemistry really. So let's get that covered, and then hopefully when we meet on Thursday, May 13th, we're going to resume the next part of the class, which is geology. Okay, so let me share with you the screen. Okay, again, these are some of the topics that we'll be covering in here. We're going to be basically discussing what the hydrocarbons are, which is, as the name probably suggests, it's made mainly of carbon and hydrogen. And then we're going to talk about unsaturated hydrocarbons. Those are where carbons can basically form double or more than a single basically bond between its atoms. And then we're going to talk about functional groups. That's basically when you have groups of atoms forming basically specific functions, such as, for example, alcohols, phenols, and ethers, and all of these things are functional groups. And at the end, we're going to close it with polymers. Okay, so this is in a nutshell what organic chemistry talks about. Organic chemistry can be cumbersome. You have so many words, first of all, so many groups, and then it can branch out into so many details on it. So we're going to just look at it from a big, basically, overview, okay? So again, it's a branch of chemistry involving the study of carbon-containing chemical compounds. Though they can be broken down into two basically sources, either organic, mainly coming from living organisms, or they can actually be manufactured in the laboratory, so industrial. So both of them are under the same classification in this case. So carbon has 4 valence electrons, so it can form 4 basically connections for bonds, and those bonds are very strong. Basically, they have very, very strong bonding energy, which means that they are very stable. That is what is so special about it. Case in point in here, if I want to form, for example, a carbon-carbon connection in here, it can give you, it can, it is going to be established with this much energy, 347 kilojoules per mole, okay? Whereas if you compare it to any of the others that involve, for example, the oxygen-oxygen bond, or the nitrogen-nitrogen bond, or the sulfur-sulfur bond, any of them is less. The nearest one is actually a sulfur-sulfur bond, and that could happen. Actually, S8 is an example for that, okay? But it is more likely to have a carbon, which is more stable, much stronger bond than any of the others, okay? So case in point, diamond, which is pure carbon, okay? So all carbon atoms connected by themselves, and it's one of the strongest, if not probably the best element that scratched any other element, is diamond, and it's used actually in the industry for digging and for all kinds of industrial applications. So that's really what it gives its strength, that strong bond that exists between the carbon atoms. Obviously, there are different basically structures for carbon-carbon in this case. One of them is this one. There is another one, which is graphite, and graphite is actually different properties than this one, but both of them have the same chemical structure, basically. So carbon atoms connect with one another through strong and stable covalent bonds. Carbon atoms are also readily bonds with many other types of atoms. So it's not just the carbon itself, okay? This provides for a near infinite number. Basically, you have all kinds of combinations because of that, okay? It's not all about memorization. So you really have to, it uses so many complicated, basically, terminology, at least in terms, but if you remember the functions, you should be okay, okay? Hydrocarbons, in addition to carbon, they have hydrogen in them, as the name, as I said, suggests. Here is one case. You have 5 carbons in here, and you have 12 hydrogen atoms in here, forming this C5H12. You have 5 carbons in here, and you have 12 also hydrogen atoms, forming a different, basically similarly looking in terms of chemical formula, compounds. As a matter of fact, there is a third one also that has the same 5 carbons in here and 12 hydrogen atoms. So all of them, you can write their chemical formula as C5H12. However, because of the way they are rearranged, so even though the number is huge in terms of how many ways you can connect carbon to other atoms, in this simple case in here, as you can clearly see, with the same number of atoms, with the same from both carbon and hydrogen, you can have different structures, different functions, different chemicals altogether, okay? So these are called isomers, actually. So what an isomer is molecules having the same molecular formula, all of them, they have C5H12, but different structures, okay? Different, basically, way that this same number of atoms are arranged or put together, okay? Case in point in here, you have the same carbon atom connecting to the other 4 carbon atoms, and in the others, no. Each carbon is connected at most, in this case, to actually to another carbon, and here is, to 3 carbons, I should say, in here, this carbon in the middle in here, but in this case, the most you will have is 2. So you'll have 2 in here, 3 here, and there are 4 in here for this carbon. Okay, this is a maximum number of polymers that you can have for this C5H12, namely, in this case, you will have 3 different isomers, okay? Now, this is a representation of the same molecules in this case. So the way that you read this one is each line where there is a node, where there is a point in here, you replace it by a carbon. So what I have in this case, I have a carbon in here and a carbon in here and a carbon in here, and a single bond between one another. And there is a carbon in here and there is a carbon in here. How many nodes do I have? I have 1, 2, 3, 4, 5. So there are 5. How many do I have in here? 1, 2, 3, 4, 5. So there are 5 carbons in here too. There is 1, 2, 3, 4, 5. There are 5 carbons in here too. And then fill in the blanks with whatever hydrogen is needed. Since this carbon in here, this carbon, first of all, has already 2 bonds, 2 electrons are already tied up, one of them with this carbon, the other one with the other carbon, then there are 2 electrons that need to be connected. For that, add hydrogen. So I need to add 2 here, I need to add 2 here, and I need to add 2 here for a total of 6, because 2 plus 2 plus 2 is 6. How many do I need in here? Since that carbon is connected also only to 1 carbon in here, I need to add 3 because I'm missing 3 in here. So there is a 3 in here and 3 in here for a total of 12. So that's how you can represent the same distribution here. So instead of calling it a structure, it's actually configuration, okay? Because it's the way it's distributed only. So it's not really a different, it's just a reorganization of the same number of atoms. So configuration is a specific way in which the atoms of a molecule are connected to one another. Or the connectivity, how is it connected, okay? So here is the number of possible isomers in this case. C5H12, you have 3, and we already mentioned them. C6H14, you have 5. If you continue down here this way, C20H42, the permutations in here, different kind of rearrangements in here that you can have is basically a huge number, 366,319. That tells you the diversity, basically, of organic chemistry. It's really can be too many. And for the same, basically, for chemical formula, this is the same 20 carbon atoms connected with 42 hydrogen atoms. You have this many different isomers, okay? That are completely different, basically, structures in here. So here is the configuration I was talking about in here. So if you're given this formula, instead of basically plugging in C in here and C in here and C in here and C in here, the way you look at this one, in each node, there is a carbon. So there is 1, 2, 3, 4, 5 carbons. So I'm gonna write it C5. I know there are 5 carbons. How many hydrogen atoms in that? Okay, because I know this is a hydrocarbon. Since there is no other, if it's oxygen, it has to be explicitly stated. If there is nitrogen, it has to be explicitly stated. If there is any other sulfur, for example, it has to be explicitly stated. The only time that is not explicitly stated is the carbon and the hydrogen. They are assumed already. In each node, you have a carbon. Now fill in the blanks, basically. Since there are 2 electrons in here tied up, and there are 2 free ones, so I need to put the carbon in here. I mean the hydrogen, I'm sorry, here. So I need to put 2 here, and 2 here, and 2 here for a total of 6. But this one has only 1 of its electrons tied up to this carbon. So in this case, I need to have 3 hydrogen atoms to make up for, basically, to compensate for the other 3. So I have 3 here and 3 here. Since I have 6 in the middle and 6 outside, so I have C5H12. Okay. One of the properties, because it's a configuration, all you have to do is just basically, I'm trying to do it with my hand, okay? So if this was my configuration, all I have to do is just rearrange this connection in here. And now I have a different polymer, or a different, basically, reorganization, if you wish, in here. So this is what we meant by it. Okay. So the question, what is the chemical formula for the following? Obviously, you have 1, 2, 3, 4, 5 carbons. Since there are 5 carbons, and the only one that is mentioning 5 carbons is this one. So this must be C5H12, okay? And you can fill in the rest of the difference. Okay, you can form, because of their physical properties, not chemical properties, physical properties, depending on where they condensate. You can actually take advantage of that and separate, for example, the organic matter in here into many different levels. And this is what is used actually for extraction, for example, of gasoline from crude oil. Okay. You have diesel at some point, you have kerosene used by airplanes, and you have lubricants, and you have the heavy stuff in here, the tar. So here is something that you need to remember. Since carbon valence number is 4, the maximum number of bonds that you can have in it is 4. It always forms 4, actually, okay? So this is the case of methane. Methane has CH4. So in this case, that's the simplest one that you can think of between a hydrocarbon, okay? However, in some instances, it may form multiple bonds, okay? So carbon always, for some of these bonds, however, may be multiple bonds, okay? So in this case, it's actually called a so here is a case, for example, this is the normal one. This is saturated, because in this case, what I mean by saturated is this case, for example, in here, you have all of the 4 electrons fully involved in a single, basically, bond. In this situation in here, so you have C4H10, but in here you have C4H 8, and the 2 in here stands for where that bond is happening. Start from wherever you want to start. So if this is number 1, this is number 2. So that's the naming convention here for the organic matter. So it's 2-butene CH, and that's the chemical formula, C4H8. Whereas in this case, it's C4, and this is an unsaturated because I have more, at least in one carbon atom, I have more than a single bond. In this case, I actually have a double bond between the carbon and the carbon, okay? So this is unsaturated, this is saturated. So a special case is benzene. So benzene in this case is actually unsaturated because if you look at it this way, you have the carbon 1, 2, 3, 4, 5, 6 carbons, and they're in this basically hexagon, or no, yeah, hexagon. So what you have in here in this case, you have 1, 2, so you have 2 potentially, 1, 2, 3, so potentially you will have 12, but you don't really have 12 because 2 of these ones are actually in a double bond, but 3 of them are in the double bond. But where are you going to put it? This could be here, this could be there, so it's actually you're going to put a circular in here, what looks like it's a ring, okay? Because they are all the same. So here is again, when you connect it with so there is a carbon in here. Remember the rule in here. So this is toluene, and this is a naphthalene, which is in this case you have 2 rings connected together. So there is a carbon in here connected to this carbon, and this carbon is connected to this carbon on this side. And in here you have 1, 4 because the chlorine is actually in. Start counting from wherever you start counting in here. 1, 2, 3, and 4. Okay, 1 and 4 dichlorobenzene. So you have 2 of them in this case. Okay, here is another example. What is the chemical formula for this one? Now I have to be careful. Yes, I have 1, 2, 3, 4, 5 carbons in here. Is it C5H10 or is it C5H12? Let's count them. I have 2 hydrogen atoms in here. I have 3 here and 3 here. That is 6 plus 2, that is 8. And in here, since there are already 1 connection in here and 2 connections in there, so I'm only allowed for 1 more hydrogen atom in here. So there is a hydrogen in here and a hydrogen in here. So if I count all of them, so it has to be C5H10. And that is because this is an unsaturated version of C5H12, okay? So again, if you go through it, that's the correct answer. I mentioned, so a heteroatom is anything but basically carbon and hydrogen in an organic molecule. A functional group is a combination of carbon, hydrogen, and heteroatoms, basically anything else, that behave as a single unit. Organic molecules are classified by the functional groups they contain. For example, this one is a pure hydrocarbon, ethane, because it's C2H6. However, if I remove one of these hydrogen atoms and replace it by the group OH, in this case, it becomes ethanol. Okay. If I don't do that, but replace it by an NH2 in this case, it's going to be ethylamine. Okay. So in this case, the function has changed completely. So this is a completely different chemical, but it's the same basic structure, which is ethane in this case. So this part did not change at all. What changed is the hydrogen that has been replaced by the group OH in here, or NH2 in this case, okay? In which of the following structure is carbon bonded to 5 times? This is a kind of tricky question. I mean, here, carbon is supposed to be connected 1, 2, 3, and there is actually a 4th one in here. Here, 1, 2, and 2 in here. This is not possible. Remember that we said that it cannot have 5. The maximum you can do is actually always is 4. So how are we going to do 5 out of this thing? So this is not possible. But all of this are possible. So this is not a possible. In which of this 5 is there is 5 bonds? Again, there is no, the question is nonsense. There is no way carbon can form 5 bonds. Okay? Or bonded 5 times. This one looks kind of 5. Look at it, count them. There is one carbon in here connected to this carbon. There is another carbon connected to this carbon. There is the oxygen in a double bond in here with this carbon. And there is another oxygen in here in a single bond with this carbon. So this carbon looks like it has 1, 2, 3, plus 2 for a total of 5. However, we know that carbon cannot do that. Therefore, this whole thing is nonsense. This molecule doesn't exist. So that's basically what you can conclude. But everything else looks fine. This carbon, for example, has 1 bond in here and 1 bond in here and a double bond in here. So that's fine. There are 4 of them. And everything else is fine. This oxygen now is connected to, at least from this side, it's fine. And this oxygen in here is connected to 2 carbons in here and so on and so forth. Okay. Here is one of the group, the hydroxyl group. Okay, that's the alcohol. Just like when we talked about ethanol being an alcohol in this case, because it has the OH, the hydroxyl group in this case. Okay, so that is how it is formed. Okay, but it has to be connected directly to the carbon in this case. So it's COH in this way. Here is methanol. We saw ethanol. This is methanol. Okay. Basically, a basis in here. If I remove this OH, I'm going to put a hydrogen in here, and that's methane. Okay. And the boiling point for it is 65 degrees. Ethanol, in this case, which has the same group OH in here, its boiling points in here is 78 degrees. That is because there are stronger bonds in here. And the more bonds I'm going to throw in, it appears to be the boiling point increases further. This is propanol, and it's 2 because it doesn't matter which way it starts. I start carbon 1, 2, so that's where the group is situated. Okay, so it's C3H. You can count them: 1, 6, and then what is this one? 7. So it's C3H7, C3H7OH. You keep the group OH by together, okay, to show the function. Here is phenol, which is really a benzene molecule replaced with one of the where the hydrogen is supposed to be connected in here with the OH group, hydroxyl group. Okay. Phenols are acidic because they can lose that proton and behave just like acids. Okay. So that's basically what that means. Just like, you know, or of course they're organic acids, and now you have this whole molecule now where that is ionized with a negative charge of -1. So this just talks about the acidity of this phenol. Now you have a thymol. You have another carbon in here. And you have the 2 more carbons in here and another carbon in here, in addition to the OH group, the hydroxyl group. Okay, the ether group has this oxygen in it between the 2 carbons. Okay, that's another group. So you have in here a dimethyl, because you have, again, 1 carbon, and that's where you sit in there. You have 2 methane, basically basic. So you have CH3 and CH3, okay? And it's an ether because of that connection in here. Look at the boiling point again, it's -25 degrees. Whereas ethanol, where is the ethanol? Here it is. has a 78 degrees boiling point because, again, it's the same strong bond in here. Whereas this one in here, the oxygen sits in between and weakens it a little, okay? So it boils at lower temperature, negative 25 degrees. Okay, you have more groups in here. So you have in, oops, you have in this case, C2H6, twice of it, and oxygen between them, okay? Now the amine groups, they have the nitrogen in this case. So here is ethylamine, okay? And that is the NH group in this case, okay? Then you have the carbonyl. Again, we're not trying to memorize these things. I'm just trying to list their properties in here. So you have a carbonyl group, a carbon atom double bonded to an oxygen atom. So that is basically what the group look like. So you have an O connected to double bond in here. So this is the ketone. And when you have a hydrogen in here, that is actually aldehyde group, which is subgroup basically of this big group in here, the carbonyl group. Both of them are subgroups, the ketone group and the aldehyde group. And then, for example, here the acetone, okay? And this is the acetaldehyde in this case. Both of them have the CH3, but except in here, this is the acetone. This is a subgroup of the carbonyl group. You have citrals in here, and again, this is some sort of OH structure in it in here. And you have benzaldehyde, in this case, also the OH in here. And it can get even more complicated. That's why in the beginning, this organic chemistry or organic chemistry in general can have a lot of basically with the same stuff, with the same basically number of protons, the same number of atoms basically. Here is DEET, okay? And carboxyl group has this basic structure in it, okay? You have an O and OH in the same time here. So you have an oxygen that is in a double bond with the carbon and which is also in a single bond with the hydroxyl group. Okay, it's acidic also for the same reasons as before, because it can lose that proton and then becomes an acid, behaves like an acid. For example, you have the salicylic acid. Sorry, I'm tired, okay, a little bit. I don't know if you guys know that or not, but I didn't have my coffee yet. And I probably will not have it until the evening sometime later. Okay, anyway, so this is this group in here. This is basically because it's, again, it can behave as a proton. I mean, it can behave as an acid because it can lose that proton. This is the ester group. Okay, again, you're not supposed to memorize this ones. It's okay to look at the references, to look at the your book, especially when it comes to questions that I hope I'm not going to pick up a lot of questions from this chapter, but you will have some, okay? So it's still try to get the main idea in her, the main themes in terms of how things are organized. Again, this is in different kinds of organization of the same groups in here. Penicillin. Again, let's talk about polymers. Polymers is a very long organic molecule made up by joining together of a smaller organic molecules units known as monomers. So you take a monomer, another monomer, another monomer. So there is a repetition basically of that basic unit, and the number can be infinite basically, not really infinite, a huge number, okay? So there is no end to the chain on this side, on the other. So that is basically what a polymer is. A polymer whose mass is equal to the sum of the masses of the monomers, so that is the addition polymer. So as long as you keep on adding, then you're fine. You're going to have, so in here you have ethylene, and so if we can connect them together, So in this case, so we have two of them. And if somehow we can break this bond, this double bond in here, and rearrange the two, now we have, this becomes our first monomer. This is the second monomer, and we can do this chain in here. So basically what happened in this is we broke that double bond in here, and now we have electrons available to connect. So now we will have connection in here, and this one is available to connect to more and more. So at the end, we will have a long chain in this case, okay? This is how it looks like. So it's the same ethylene that you started with that is repeating itself time and again now, okay? So this is the basic unit that is repeating now everywhere. This is the monomer, and the entire thing is polyethylene. So it's the same thing that is repeating. Same thing. We have two molecules, each and every one of them is a propylene. So when you rearrange this ones in here, with the carbon in here basically broken down, this double bond, and you will only be left with a single bond, and you connect them. Now, all of a sudden, you have polypropylene, where the basic monomer is this one. And you can have very long chains, okay? That is part of the things that is great about organic chemistry. You can have all kinds of different organisms, same stuff in here, okay? Case in point, you have Teflon. It has some interesting properties, especially because of the how fluorine reacts with other matter like oils and things like that. So we use it, for example, on cooking utensils, cooking, for example, pans, because it doesn't stick. So it actually, it's good for this thing. So it has some chemical properties that are very useful in this case. How can we make it? One way of making a polymer is through the condensation process. And the condensation process formed when the joining monomers unit is accompanied by the loss of a small molecule, such as water. So in the first case in here, all we did was rearrange just the bond in here, the double bond that existed before, and now we have a polymer. Instead, what we could do is lose a small molecule, such as water, for example. Here is a case for that. So we have this long chain. This is hexamethylene. At the end, you have the amine function, okay, and H2. So there is carbon everywhere in here and hydrogen. And this is an adipic acid. Again, you have the OH function in here. So what you do in this case, if you take this hydrogen, I mean this group OH, and this hydrogen, and get rid of them. So now you're going to have the oxygen in here in a double bond. This oxygen is gone, by the way. This hydrogen, one of them is gone. So you'll be left with one hydrogen and an NH in here. And this can then be repeated, okay? And all of a sudden you have nylon. Okay, so that is basically the magic of organic chemistry. As long as you repeat this one, so you have a blueprint on how to repeat it now, okay? But it lost H2O in the process. And like the first one, where it was a rearrangement of the bonds, this one actually, you lost part of the molecule in order to form this long chain in here. Again, you can continue this process until you have all kinds of organic matter. Here is the beta carotene. Actually, nature does it too. So many of the natural products, molecules by plants are formed by the joining together of isoprene monomers via an addition polymerization. So basically you just add, you keep on adding until you get this very long chain, for example, for the beta carotene. Okay, I really intended for this lecture today to be a summarized version of the entire thing for the organic chemistry, at least part of it. As I said before, in terms of the exam, this chapter will have very little, because otherwise it could be ugly because of the different terminologies in it and the different words and things to remember. Okay, there is nothing current for today. Okay, So it's not graded today. So that is really the main topic that I want you to guys remember from this one in here. Hydrocarbons, you have hydrogen and carbon. The carbon, the fact that it has many ways of connecting to different atoms, especially hydrogen, and how stable that bond is, and then how at the end you can end up with very long chains, which are the polymers in this case. Okay. So that's going to, please watch for tomorrow. Today, it's not possible to publish anything because I have classes throughout the day. I have meetings actually. Tomorrow in the morning, I have a meeting with the what is that? The space grant students from NASA and UCSD. So we're working on that tomorrow morning. And then in the afternoon, I hope to publish your review exam. The review exam should be available tomorrow afternoon until Monday evening. And so please take care of it, hopefully Saturday, Sunday. And Tuesday, we have an exam. Exam is chapters 14 through 19, including this chapter today, albeit, like I said, this chapter is not going to be emphasized, but the previous chapters are. Okay? Makes sense to you guys? Okay, very good. So I'm going to stop recording. Very good. I'm going to stop recording. And